In this lesson, we will learn how to calculate the required pump head for a system given a variable flow rate. Typically, when designing or selecting pumps for systems, it is common to assume steady, uniform flow. This means that we can apply the energy equation for steady uniform flow in our control volume. Now let's assume we have a simple system with only one pump and no turbines, so we can eliminate the turbine head. Looking at this equation, we can separate this equation and divide it into the pump head term on the left and everything else on the right. By rearranging this equation, we will have the following form of the equation, which has a pressure differential term, a velocity squared term, a potential term, and the head losses. We know that head losses are a function of friction losses and minor or component losses. We also know that for uniform flow, the velocity across the control surface is equal to the average velocity, which in turn can also be calculated by dividing the flow rate over the area of the control surface. Since our flow is steady, our flow rate should be constant throughout the entire control volume. This means that we can express all the velocity terms in the energy equation as functions of flow rate and area. Note that in this system, we're assuming that the velocity throughout the portion where the losses are occurring is constant as well. Taking this equation, we can now separate all of the flow rate terms. This will give us an energy equation with two terms that do not relate to flow rate and two terms that relate to the flow rate squared. If we rearrange all of the non-flow rate terms on one side and all of the flow rate related terms on another term, we can assign them the coefficients of C1 for the non-flow rate related terms and C2 for the flow rate related terms. This will give us a simplified expression for the required pump head of a system of pump head equals a coefficient plus a coefficient multiplied by the flow rate squared. Looking at this equation, we can have an idea of what this would look like if we were to plot it in a graph. It's very common to assume that the coefficients C1 and C2 are constant. However, this assumption does not really apply for all situations. Take the coefficient C2 for example. C2 includes the friction factor in its terms. And we know that the friction factor, if our flow is not fully turbulent, will depend on the Reynolds number, which depends on the velocity, which in turn is a function of the flow rate. This means that as our flow rate Q changes, our coefficient C2 may also change.